Hello everybody, welcome to the next video in our Fusion Zero to Hero series. Today we're going to be looking at the simulation options that are available to us in order to begin to optimize our designs, taking the parameters, the parametric modeling, and potentially some of the configurations, and seeing which of these different configurations work better for different sorts of design intents. So we're going to be looking predominantly at the impeller, but we might have a quick look at some of the options that are available potentially for the encasing as well as we go through. First half is going to be looking at setting up the different studies that are available to us, and then the second half also we'll be looking at the results that we get from those studies. So as we've mentioned before, we're going to go straight from our design environment into the simulation environment in order to get these results and to start setting up the studies that we're wanting to have take place inside of our models themselves. So I'm keeping to a 3-blade, maybe even a 4-blade. I'll quickly switch to a 4-blade configuration of the model itself. So going for a 4-blade configuration with similar impeller and blade heights to begin with, and including the splitter blades as well. So we've got if we're following on from previous examples, we've got the thicken 2, which is our splitter. And we are enabling it as part of the process as well. Just as a note, we could rename those features as well, just to make them show up a bit neater inside of our configuration table, for example. So for thicken 2 over here, bit of a side note, but I could right click and rename it from within here. And I could call this one the splitter blade, or just splitter. And then maybe this one I'll call primary. Not edit the feature itself, rather renaming the feature. And this is going to be the primary. That should then translate into splitter from within the configuration table. So if you are wanting to change any of the names from within the table, it's worthwhile changing the name of the feature itself that it is representing or driving, at least from within. The other thing I will very quickly change from within this configuration, the other thing I do want to change rather than the parameters in the configurations themselves, is actually the material of configuration 1. So I want a 4-blade and I want theme to the aluminium for this particular study. So now that I got the configuration that I want to create a study on, I'm going to go and switch over to the simulation workspace using the workspace change option, or the change workspace option, and going down to the simulation workspace from within the Fusion environment. We then met with the standard, for those of you that are familiar with it, and for those of you that are not familiar, the standard introduction, or standard options rather, into the simulation environment if we do not have a study that exists inside of the environment, where we can come and choose the different study types. Now, depending on your subscriptions, depending on the licenses that you have for Fusion, you might need to pay for some of these or not. For static stress, at the time of recording, this isn't requiring any licensing. It doesn't require any credits, but for most of the others it will require some credits, or if you've got the simulation extension, you've got the ability to make use of any of these studies as many times as you want to. So we'll start off with a modal frequencies analysis on the component. For those that might not know what a modal frequency is essentially what we'll do against this model itself is we're going to vibrate it, we're going to shake it as part of the study, and we're going to be able to see if based on the operational frequencies, whatever natural frequencies this component is going to encounter over its lifetime, whether it will be able to withstand those. So every component, any material has a natural frequency to it, and based on its shape, that frequency then changes and is then dispersed throughout the component itself. And we essentially just wanted to test what the frequencies are of this component in its current configuration, whether it needs any thickening or thinning out along the way. So to get this one set up, and same process throughout the rest of the environments within Fusion, we begin to work from left to right to make sure that we are getting all of the details that we need to as part of the process. So we've already created a new simulation study, and that's essentially what would be the first button available to us. If we want to, as we will later on, create a second study, we've got the ability to create a new study from within here. We then want to simplify the model within this current study. Anything that doesn't need to be considered as part of the study. In this case, we've got those two surfaces that are driving the blades themselves, but they don't need to be considered as part of the study. So going into the simplify option, we can then begin to go and remove any components or any features, or potentially add features to the model itself that might need to be taken into consideration. If you're only wanting to look at, for example, the root of the component, we could go and remove all of the features that are the blades and look solely at the root. And we could go and simplify anything, removing features, removing faces. We could fillet some features, remove or add chamfers, combine, split, and any modification, but this only takes place on the simulation model rather than taking place on the actual physical model itself. So this is simulation specific. So in this case, what we're going to do is look at the model components, and we've got the two surfaces over here. I'm going to right click and remove them over here. So we've no longer got those surfaces, and it's not going to take that into consideration. Generally speaking, the simulations don't like working with surfaces unless they are already meshed and are considered part of the study. In this case, it would be giving us some conflicting results along the way. The next area over is the study materials, the materials that we want to study against this. So if we haven't already assigned a material, this is where we would go in and assign that. If I go and look at this now, it's automatically set to same as model, which in this case is aluminium. And I've got exactly what I want. I'm wanting to study this against aluminium, so this is perfect. If I wanted to change this to a different material, I'd change the study material option that's available to me. I could go and change to any of the materials in the material library within Fusion. We can also establish what we're wanting to use to calculate the safety factor. So are we looking at the yield strength of the component, of the material, or are we looking at the tensile strength, the ultimate tensile strength? And based on the two that we choose then within that, are we looking at the yield point of the material, or are we looking at the tensile strength of the material? We can then begin to work out the safety factor from within there. So if we want something a little bit closer to the results, or want to bump up the safety factor a bit, we'd potentially be looking at the yield strength for the material itself. The next tab over is looking at the constraints. So we've got a few different constraints available to us depending on the type of constraint we want to apply. Whether we want to have a rigid connector, which is just going to make sure that it has certain points that cannot move. We've got bolted connection or bolt connector, which is just going to allow a certain bit of pivoting around it, but it's going to allow bolts, wherever the bolts are, to use those as connection points to allow some movement if we wanted to. Otherwise, we've got the more traditional structural constraints, which will have a few different configurations to them, whereby we've got fixed constraints, pin constraint, frictionless, described displacement, or prescribed displacement rather, and a remote fixture, or remote constraint rather. Fixed constraint, for those of you that don't know, will just lock all degrees of freedom, or give you the option to allow certain degrees of freedom, but naturally, or by default rather, this will be a full fix. So this particular surface cannot move whatsoever. And this is really important from studies. We need to have at least one surface that cannot move and everything else moves around it to be able to study how the body itself would react to certain forces. If there was no fixed surface or any surfaces that weren't moving and it was completely free to move, it would just be able to move throughout the model, and it wouldn't give us the results we're wanting. So we want to ensure that in this component itself, the forces are enacting on all of the other surfaces except for one, and that one force is essentially, or that one face rather, is locked in space. For this particular one, what I'm going to do is I'm going to use a pin constraint. What a pin constraint will do is it'll allow rotation around an axis, but it will not allow it to then move from the position that it is in that particular location. So I'm going to go and grab the hole in the middle, which is going to allow rotation around that, but it will still allow it to move up and down if we allow it to from within these options. So we can allow axial, or we can lock the axial movement from within, and we can allow or disallow radial movement throughout. If we have a tangential surface, we could also allow tangential movement or lock the tangential movement as well from within the pin. Once we've got that set, the next thing we want to potentially do is add a load. If we want to add a load on top of the study, which this again is the modal frequencies. So if we know that the particular component that we're looking at during operation will have another load on top of it, or will have something dampening the movement during the vibration during the modal study, we would then be able to add a structural load as well if we wanted to. In this case, I'm going to leave it without a load. The contact section is predominantly for the assembly environment. So if we do have multiple components and want to ensure that they know that their relationship is intact, pretty much like creating a joint and so on. If you're familiar with the assembly environments, we'll do a video later on about assemblies. But if you do want to establish how two bodies engage with each other, this is where contacts would be established. Within the display options, we've got the ability to view the degrees of freedom of the component itself. So I can see that at the moment my component is partially fixed. This is especially great when we do have multiple bodies. We can then start to visualize which bodies are fully constrained and which aren't. And a fully fixed component, in this case this one won't be, because we are allowing some rotation around the pinpoint itself. So it's not a fully fixed one, but we can change the color scheme that is associated to this as well if we wanted to. We're going to go straight from here though and begin to do a quick pre-check. It's usually great to do a quick pre-check beforehand. This little icon will change based on how ready your study is for solving. So if I didn't have certain elements to this, potentially a material or something, we'd have a little warning mark. You'll notice that one come through a little later on. And if you do have any issues in here, orange for warning, red for an actual issue, as an error rather. So we've got the three levels of configuration. If I hit OK, or if I click on this rather, you'll see this one's ready for study. So there aren't any required features or required inputs before we run the study, and we can essentially just go ahead to the solve. This will go ahead and confirm which simulation we're about to run a solve on. And if you do not have the simulation extension active, which I do in this case, it will tell you how much this particular study will cost in terms of credits. In this case, again, I've got the simulation extension, so I'm just going to hit solve study on this one. This will then go ahead in the background and start to run those studies. It's going to upload this to the cloud to then go and do that, and we'll get a little status bar in the background. That is also available to us within our little job status over here. We can go and view job statuses, whereby we can go and view any data or simulation, generative design, drawing information, or automated drawings and so on. So if we ever want to check that, what's happening in the background, we've got that available to us. While that is going and creating that study and simulating that, I'm just going to very quickly create a new study. And the next study I want to have a look at is some of the structural buckling of the component itself in load. So we've got a structural buckling option available to us. Again, this is part of the simulation extension. And this is going to have a look at, while we're applying a load, how much buckling there will be in the components themselves. So using the structural buckling, I'm going to go and apply. First thing I'll point out is we've got a pre-check, which is red. It's telling me that there's some information that is required as part of we've got an incomplete setup. And if you ever are unsure what's required, we can just go into this menu a little bit and see that we require a load, we require constraints, and there might be some other forces in the settings, some rigid bodies and so on that don't have anything associated to them. These should start disappearing as long as we're working through and clearing out and adding the information that we need. So again, we've created a new study. It is the structural buckling study. We've got a simplified model. I've removed those surfaces. It's remembered that from the previous setup. In the study materials, we've got the material that we want as part of the process. The next thing we want to do is go and apply a constraint to this. So again, I'll probably go in and grab that same pin constraint because I do want some rotation in here, and grab this central axis over here as the location at which I want to lock that in. The next thing I want to do is apply a load to this. I want to, in order to study the structural buckling itself, I want to go and apply a load that's going to be set to this component. And the loads that we can go in and apply are either going to be a structural load itself, so loading onto the component itself, or we've got also the ability to apply an angular global load to this, which is going to represent the centrifugal or tangential forces enacted against the component. So I want to go and apply this to the component itself to make sure that it is rotating, and I want to then be able to see what the structural load is against this component from there. So from here, we can then go and choose what type of direction we're using, whether we're going directly in a single direction on a particular surface, or in this case, we're going along an axis. And that axis we can then go and establish from within here. So if I say that the axis is this outer area over here, the outer surface, and we know that if we know the velocity that this is going to be rotating at in degrees a second, we've got the ability to go and apply this. So if I say, for example, so we've got a fairly low speed on this particular one. We've got about 800 rotations, RPMs, or in this case, this is in seconds, but we've got the ability to change the units. Rather than going for degrees a second, we could go degrees a minute, radians a minute, degrees an hour, radians an hour, and so on. So I'm going to go degrees a minute and say that we've got about 800 RPM on this one. So it's 800 multiplied by 360. If you didn't want to do the math, and you've got the ability to then just hit OK on there, and this will then take that into consideration. So we now have inside of our loads, we've got our angular load available to us, which is giving us the magnitude in there. All that should be left now, we've got a bit of a warning. Let's just check the pre-check to see what that is. And the thing is, the structural loads are not defined, so we still need a structural load against this component, although we do sort of have one there. I'm just going to go and see if it's going to let me solve this. It is going to let me solve this. It doesn't have a load applied to it, but it does have a force applied to it. So if we do want to add a load on there as well, we've got the ability to do so. I'm just going to use just the force on its own as part of the study. So I'm going to hit solve study on this one once more and run through it this way around. The last one I want to do, again within the new study, is I just want to test a static stress on here. If we go and apply just a single stress on the component itself, we want to be able to see how it's going to be able to withstand anything. Let's say, for example, we've got a bit of pressure on the model itself from the top down. We want to go and apply that through. So hitting create study on this one, just with a static stress. This time around, I want the central axis to remain as it is, and the bottom plate itself, I just want to be able to apply a load or force down onto the component itself, just to see what would happen if there were some compression applied to it by a mechanical force of some sort. So again, throughout the process, got the simplification of the model fine. I've got my study materials fine. The constraints that I want to apply are a fixed constraint to the bottom of the part over here. So there's no movement whatsoever on the component. And I might actually say that in this case, I'm not going to worry about the internal, the hole down the center. If a force is being applied on there, I want to be able to see if there's going to be any warpage or any buckling rather, on the inside of this component. So I'm going to go and apply a load, a structural load against the top face of this part and see how that's then distributed. And again, we've got a force that we can go in and apply, whether it be a pressure, whether it be a remote force, a hydrostatic remote moment, and so on. In this case, it's just a force on that normal to that face itself, and it's going to be either measured in newtons, or I can change the units here and go for a pound of force, an ounce of force, a ton of force, and so on. So I'm going to measure this in newtons, and roughly multiply a kilogram by about 10 to get a newton in there. And let's say that we're going to apply a force of about 50 kilograms, so 500 newtons. Again, once I'm happy with that, it's got everything that needs inside of the pre-check, so I'm going to go and hit solve, and now I've got a third study running for me. I noticed the one job failed, and we can have a look at the details of that as well. So we've got two studies that have completed now in the background as we've been going and applying these studies to it. So I'm going to go and quickly have a look at the results of my modal frequency study on the component itself. And we can see this is looking at the frequencies that this particular component is going to be able to withstand. So natural frequencies, if this component is at this frequency for long enough, it has the ability to start to warp and to do things that we don't necessarily want it to. And so essentially what we're looking at on within the study itself are certain frequencies that we want to try and avoid during the normal operation. So if we know that this needs to run at 700 RPM or something like that, that's potentially the frequency that it's going to be moving at. If it's going to be on any, like, again, this is going to be on a compressor, or potentially on a compressor, and if there's any vibration in the motor or the engine or anything like that that's going to be operating at a certain frequency, we want to try and avoid those regions along the way. So if I have a look at the mode drop down here in the results, I can see that the frequencies that we need to try and avoid start at 6,494 hertz, and we'll get this is an area that we want to try and avoid in terms of this is a natural frequency that it hits, and we can see it hits it twice within quite a short succession. So 6,494 as well as 6,502. Then there's a bit of a gap until 6,947 and 6,958. We then have those in there as well. The displacement is a little bit disorientating, and don't worry too much about the actual displacement in here. That's why it's been set to 1 as a maximum. It doesn't mean too much. It's not exactly how much it's going to deform by, and this isn't exactly what the deformation will be. But the important thing when we're looking at these studies is the actual frequency itself that we need to worry about. So we've now got a result of all of the frequencies that we might want to begin to avoid as part of the process itself. The other simulation we created over here was the structural buckling. I'm just going to go and have a look at this one very quickly. So the results were inconclusive. It didn't have any proper results along the way. We might want to then go and change either the load or the constraints around it. It did warn me in the initial one about the fact that it doesn't have any structural constraints along the way. So we might want to go and apply some structural constraints as well against the component in order to run this a bit better. So we can come in and either apply a bearing load against it or a moment against it as well. Maybe a remote moment or so on. I'm just trying to have a quick look. Potentially a bearing load on this one, although what we do potentially want to have a look at might be a case of actually just locking down the pin constraint a bit more. So rather than just a pin constraint, I might go and add a second constraint to the bottom face. Now we don't want the bottom face to remain still where it is. We want it to be able to move, but we don't want it to be able to translate. We don't want it to be able to move up or down. So what we can do is go and apply a frictionless constraint against it, which is not going to allow any friction between the surfaces or allow any or reduce the movement that's able against the component, but it will just make sure that it stays in one single position laterally in this case. So if I hit OK on there now, that should hopefully give us a better indication, which we do over here. So it's probably just a case of realistically just locking down that pin constraint, but we want that pin constraint to be able to rotate around, and we don't want any movement further down a particular point. So we've locked degrees of freedom against this component a bit more. If I have a look at the degrees of freedom, it's now at potentially fixed. So it's not fully fixed because we do still have the ability to rotate, but it's mostly there as part of this process. So I'm just going to go and recreate that study as part of this process and let that run through while we then go and look at the final results. Oh, I guess in this case we'll come back to the structural buckling in a few minutes as well. The next one over is the static stress once more. So I'm just going to go and look at the results of the static stress, activating this study using the little dial and looking at the study in here, and we can see that we've got a really high safety factor. We've got more than 15 on this particular one. So that load that I applied of 50 kilograms, this particular component can then handle a lot more than that. So the recommendations from Fusion as part of the study are either use shape optimization and reduce the shape a bit if you're wanting to make sure that this isn't over-engineered, or try using a weaker material, less expensive material as part of the process. Now, it's aluminium, it's not super strong, but we could potentially reduce some of the thickness of the component itself if we wanted to, or we know, actually, let's run this with a higher magnitude, and we can go in and adjust it from within there. So yeah, realistically, we've got a fairly strong component over here. There doesn't seem to be much, if any, buckling anywhere throughout the component. It's got a maximum and a minimum safety factor of 15, meaning that it's more than capable of handling that force. But other areas we can begin to look at in a static stress is where the stresses themselves will be concentrated, and therefore the distribution of stress in the component itself. And this is looking at the moment at the von Mises study using megapascals. So we've got 18 megapascals as our maximum stress, and we can see the areas where the stress is at its highest, as we would expect, is where the blade is coming out. It's right in that corner. If we were to push that down, that's the area that would feel the tension the most, or the stress rather, the most. We can also start to bring the areas down. We've got a volume in here which is colored based on the stress that's associated to that particular part of the surface. So if I say, well, I'm not worried about anything that is below 8 megapascals, so I'm going to reduce the area that it shows me within here. We can then start to remove any material that is less than 8 all the way up to that point over there, and I can see that most of the stress, as I would probably expect, is where the force itself is being applied. So we've got a really small surface area that's absorbing all of the 50 kilograms on there, and then distributing that very quickly throughout the component itself, and it reduces, as we can see, very quickly as it goes throughout the rest of the part. Other areas we could have a look at are displacement. If we do start to see that there's going to be a lot of displacement, and I can see there's very minimal displacement as part of that process. Again, most of that will be distributed within the first portion at the area of, I guess, impact, the area of contact. And then if we do have any strain, where that strain is, and we can begin to, again, have a look at each of those different environments. We could also use some of the tools, some of the inspection tools, to highlight or hide the minimum and maximum areas. We can create point probes as well. So if we are worried about a particular surface on the model, we can use our point probes to begin to look at that. And if we are looking at any reactive forces, we can have a look at and establish where those are based on certain entities. So if I have a look at this outer surface over here, there's no reactive force at all. Whereas if I have a look at this one here, it will usually be showing a decent amount on there. Let me just try and grab something here. I guess these are all minimal, so it's not showing me much at all. So realistically, we want to increase the load on this particular one. Then I should hopefully have some results in the structural buckling. I'm just going to go and activate that one very quickly and see what we have. So we do have results this time around. There's no failure in this process this time around. And we can see that the displacement itself, its maximum displacement, probably as we would expect, is going to be towards the outer rim of the component itself. And what we can also then view is the X, Y, and Z displacement as we go through. So it's not giving us a lot in terms of values in here, but we can see that the area where we're going to be potentially needing to look at the buckling on is right towards the outside of the component itself. And we can have a look at the different values against the load itself. So based on the load that we've applied, we can then multiply that load as well. And we can then start to see other areas that might be affected by this this force, this rotation, and we can start to see that actually on the smaller blade over here at minus 248,532, at mode 2 we've got that force on there, and at mode 3 we've got that on another blade over here. So these are the areas that we'd see the maximum buckling as we go around. And depends on rotation and all of that as well as we go through, if we ever wanted to have a look at different rotations and so on. So probably could go and increase that velocity if we wanted to for this particular component once more. So again, probably got a bit of an over-engineered component, but that's mostly because we want to have as many blades as possible, and those blades will be adding a bit more structure to the component itself. And we've got a fairly thick root on the component itself as well, so nothing too crazy to worry about here. Again, we could probably increase the velocities and so on, and get a bit closer to a higher frequency in the studies themselves. So yeah, that's a quick look at the options that are available from the simulation environment within here. There are a few other options that we could potentially look at using either generative design or the like, in terms of the encasing, potentially trying to optimize the flow of air or fluid that's coming through here. Using inside of the generative design, we've got a tool which is the fluid path. I won't go over this one now. We're kind of running out of time a little bit on this one, but beginning to have a look at how fluid would want to flow through and between two surfaces, especially if there is an obstacle in there. We can then begin to optimize the surface area of that flow itself as we go through, creating a start point and an end point along the way. But other than that, that's pretty much all I wanted to have a look at for this episode. So thank you very much for your time. Hopefully that's been a little bit insightful. And we can begin to then have a look at how we can take this information through to the actual manufacturing area in the next episode. Otherwise, thank you for your time, and I will see you all in the next one. Bye for now.